Severe plastic deformation. This is the last method for nanomaterials elaboration by mechanical means that we are going to consider. In this term, severe plastic deformation, also called SPD, we find a full family of methods like equal channel angular pressing, ECA, angular torsion, or pack rolling, which brings the possibility of continuous production. Methods which have in common that there is a plastic deformation of the original material through mechanical means, which is going to give the possibility to reduce the size of the crystallites that compose the polycrystal material. So in equal channel angular pressing, a bar of the material is pressed through an angle in a die. In the angular torsion, the material that is going to modify suffers from a plunger the torsion while applying a pressure. In the pack rolling process, two rolls here are going to compress a material that can be afterwards fold and again roll it again. Here you can see examples of the ECA method, the equal channel angular pressing method. Here you see the piston, and this is a half of the die in which we can see the sample that is going through. So you need to close the other half and then to press the sample through it. This is an industrial pack rolling machine. In the ECAP method, the sample, when going through the angle while pressed by the plunger, is going to suffer an enormous shear. It is easily seen in this scheme in the right side. You see the sample is having this form when arriving to the angle, and after going through is going to adopt form number 2. So if we compare form number 1 and form number 2, we realize that form number 1 suffers a shear in this direction to finally get this shape. As a consequence, the microstructure of the sample is going to be very much textured, that is observed here, and this is the result of the one directional shear that can be evidenced through diffraction in the different planes of the bar. One way to obtain a more homogeneous texture of the sample is to go through successive pressings, and this is one example. The sample here is pressed through this channel, then the die is turned here and press again in another direction like here, and then again turn and press in another direction, and this you can get more homogeneous texturing. As a result of successive pressing, the nano size or the size of the micro nanocrystallites of the sample is reduced. So here, for example, you have the initial size distribution in nanometer scale of the sample initially used, and after 2 passages we see immediately that we have already reduced the mean size, and after 12 passes we get a distribution that is much more sharp and centered at much smaller crystalline size. There are many other geometries to apply ECAP, for instance going through the complicated pipes like that, or you can have dies with a double press in one side and the other, so you can press first in one passage, again go 1, 2, 3 many passages in the same channel. It is possible also to combine rolling and ECAP. This is very interesting because this allows for a continuous production of a material with different characteristics. So you see here arriving a thin strip of the material guided by the rolls, and then going through equal change angle here by this pressed by the rolls, and in that way the obtained sample has a different microstructure or nanostructure. This can be also done in this way here. Some applications of nanostructural metals and alloys are, for instance, in the motor industry and aviation, where light alloys are needed, because then that way you reduce the weight of the planes or the cars, and you get you need less use of kerosene or whatever energy resource you are using. It is also much used as to obtain refractory metals with higher strength for advanced shape memory, with advanced shape memory effects in space medical applications. For instance, for medical applications, you can have implants here that you can see in a bone. This is an implant for a spine or for a correction of the spine, and these materials you need to be light and with able to resist to deformation. So if we want to synthesize what we have seen, we have distinguished high pressure and high temperature methods. With these methods we can go through very large thermodynamic excursions to very high pressures, high temperatures, but most of the time the volumes are very small. Even when we call large volumes, the volumes are just at maximum of the order of cubic centimeter. So you need a very important added value for industrial application, and this is the case of diamond or super hard materials. So these methods allows also for exploring a lot of chemistry paths, and this can be a way to determine targeting materials that can afterwards develop it with other methods. The milling methods can modify the morphology, the composition, by allowing, for instance, the structure. They need the consolidations through sintering or hot extraction, and can be applied at the industrial scale. This is the case also for severe plastic deformation, which allow also for continuous operation and can play on the crystalline morphology, size and texture of the crystallites. And that's all.